Okay, so we're just going to go over some of the content of the workbook. This is sort of I've cut up the note that was there in the key ideas section, and just wanted to kind of explain a little bit of it in case it's not super clear. I did want to leave the wording that they used in because it's good mathematical wording, and you should get used to reading that as well. So this is going to be investigating the properties of circles, section 7.5 from the workbook. Now I'm going to move ahead here first. I just want to go over what I think is sort of the most important. This here. This is probably the most important section. The others we'll get to in a second, but I just want to cover this. I have a geometry sketchpad open. I'm going to kind of run through it. So I'm not going to read through this, but you can obviously see what it says. And again, a lot of mathematical wording. Essentially what it's saying is, sort of here's a more English friendly summary, that basically starting from AB here and going to the center of the circle will always give us an angle double what we get if we go to the edge of the circle. Okay, so the angle from AB to the center of the circle is double the angle at C. And that's regardless of where C is, provided it's above AB. Okay, so if I pull C all the way down here below AB, that's not necessarily true because now we're not going the same direction as the center. So that's sort of what that's trying, or what the stuff above is saying. Following that same idea, if we have two chords of the same length, so here we have AB and CD, and the angle at the center is going to be the same as long as AB and CD are the same. And it kind of makes sense because what we have here are radii here, 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 and here. And so we end up with two exactly the same, two congruent triangles. And obviously if three sides are the same, the angles are the same as well. And then by extension, knowing that that angle is double the angle from AB to the edge of the circle, which is the diagram over here, the angle here and the angle here must be the same as well. Okay, so that's sort of two chords of equal length, AB and CD, have the same side central and inscribed angles. And again, the idea behind the central angle makes sense because it's a congruent triangle here to here, exactly the same size in every way. And then by using this argument, the angles here and here must be the same. Okay, so I just sort of wanted to show that. Certainly nothing fancy, but as I move C around, I've got the computer measuring here the angles, and you can see there's no movement at all in the size of the angle. If I did switch, if I started moving A around, 124, 62, the decimal place is off, but that's just because the measurement's not perfect. Basically what we've got is this angle, this angle will be double this angle as long as we're moving around the outside edge here, and there's no change in what you see. I should have kept away the last decimal place, I guess. If we do drop this one down here below A, now all of a sudden my angle's changed. And you can see clearly the inscribed angle is not anymore double what the central angle was. But again, as soon as B gets onto the other side of the center, which would be back at that point again, 172, 86, basically double. Now, one interesting thing that we just kind of went through here, this is one of the other rules that I haven't yet shown, but if we have this, I can't quite get it, I had it. If we have chord AB going directly through the center of the circle, that's right around there anyways, what happens is the angle at C, of course, I mean just kind of by extension of what we just saw, the angle now, if it's A through O to B, is 180 degrees, then my inscribed angle down here at C must be 90. So as long as we have the chord going directly through the middle of the circle, the inscribed angle in the corner is going to be 90 degrees. Okay, so that's just kind of an extension of this. It is one of the other rules. It's probably, yeah, so it's the last two things, I'm kind of going out of order here, but are just kind of follow-ups to that. So if I have any 2 points on the circle that have the same AB chord down at the bottom, the angles will be the same, and that's just kind of an extension of me rotating the C value around. And then the 90 degrees here if AB goes directly through. So if we have 180 here, clearly we have to have 90 up here. Okay, so those are sort of the key ones. I will go back up here and just kind of talk through some of the easier ones. So this one says the chords in a circle are equidistant from the center and equal in length. So basically, I think the diagram tells it maybe a bit better. If we know that AB and CD are the same length, then we know that the distance from O to there at a right angle. Distance is always the shortest distance when we talk distance in math. So at the right angle, we're going to get the same distance here as here. The reverse, of course, is also true. If we know that we have a right angle here and the same distance, then we can conclude that AB will be the same size as CD. And again, it sort of comes down to just a matter of what we end up forming. My pen is not working. Okay, there we go. What ends up developing here is if we did join these, and that was a bad idea. If we join these, what we see is we have 2 radii here, and we have a common height with a common right angle between this triangle and this triangle. And so if we have this length and we have this side and we have a right angle, then we can calculate this value using Pythagorean theorem. Obviously this value here between C and the that point right there will be the same, and the same idea over here. So what's forcing basically is that we've got enough information there to have a triangle that we could calculate with trig, and of course the calculation would be the same in all cases. Same idea over here. If I did extend my lines out, because they are all the sides of the triangles that I'm drawing are radii, I end up forcing the triangle here to be calculatable, and then of course I'll have the same values for all of them. Moving forward, let's see. If a line from the center hits a chord at 90 degrees, it cuts the line in half. Sorry, cuts the chord in half. Okay, so that's basically what this is saying. And again, a little bit wordy perhaps. Read through it though, do understand all the terms. You should be able to recognize from the terms, from the red description and from the diagram what each term means, and sort of be able to understand when you read something like this what we're actually describing. But basically we're just suggesting that we've got a chord AB, we have a line coming from O, and it's either it's hitting at the center of AB, which means that this will have to be a 90-degree angle, or it's coming out at 90 degrees to AB, which means that it has to cut it in half. So again, either one forces the other. If I tell you for sure that is a 90-degree angle, then you can conclude, so it's cutting AB in half. If I tell you it hits the middle of AB, then you can conclude it must be a 90-degree angle, and you can use that however that might help you in solving a question. This one's pretty straightforward, I think. If you have a tangent to a circle and you have a radius from the circle, and they're meeting, if they actually connect, they're connecting at 90 degrees. And I sort of put, tangents to radii meet at 90 degrees or not at all, because of course it's a little silly, but I could draw that tangent right there, and clearly the line from O going out this way, this radii does not actually hit it at 90 degrees. So that's sort of the idea that if this is a tangent and they are actually connecting, and this one's not going to look great, but if I've done a decent job with my tangent and I've done a decent job with my radius, then they'll actually hit at 90 degrees. That's fairly close, although again, just not perfect because I'm not perfect. And I suppose my line should have, my tangent should have arrows on it. That's not what I want to do. Anyways. So any point outside of a circle can have two tangents drawn from it. So if I put a little point out here somewhere, wow, what am I doing? Sorry guys, my brain's not on this morning. Okay, so if I pick a point out here somewhere, wherever it happens to be, I can then draw two tangents from it that will make contact with my circle. And this is again just what the rule is actually telling us. And if they are actually tangents and they're drawn properly, then where they make connections, the length will be exactly the same. So from here to here, this distance and this distance will be identical. And that's regardless of where that starting point lies in space. So if I just do a kind of extreme version here, if I start with my point, just say down, way down here, I will have the same thing, even though it looks like it's sort of on this side, because what's going to happen is my my tangent over here will just kind of make up for it, and you can see that they look pretty similar in length, and of course if it was drawn properly they would be exact. And so I think that's pretty much all the new rules, laws, whatever you want to call them. Basically you'll be making use of those facts. They are facts. Okay, so once you know one of the pieces of information in the question, they can help you determine any of the others. If I know that AB, in this case, I know that I've got this diagram, then right off the bat, I know the angle in here will be the same. And if I had this angle to deal with, AOB, I would also know that it's double those ones. So once you sort of recognize the diagram, you see what you've got, you can use any of those facts to either finish it up, to solve it, to do whatever it is you need to do.